Hey, so this lesson we're going to talk about logarithmic differentiation. So last lesson we talked about exponential differentiation and how to find derivatives involving some sort of exponential function. So today, on the flip side, we'll talk about functions that involve logs or some sort of logarithmic function. So either regular log or natural log or something like that. Before we actually get into that though, I want to give you a warm-up problem that deals with exponential functions and then finding derivative. So this is stolen from a past AP test. So your job is given this function that, by the way, is not an explicit function. So it's something that's an implicit function, which means that we need to differentiate implicitly to find the derivative in terms of, and you can kind of see, and sorry my writing's small, but you can kind of see it's in terms of x and y, so you don't have to necessarily solve for your y function. We're finding it in terms of both those variables. So I want you to pause the video right now and try this problem and see if you can get the right answer. So what we should see is that you should end up with your correct answer of D, but I'll show you how to actually get there. So if I was dealing with this problem and I was finding this derivative, I'd have to again do this implicitly. So my first one here is a product rule because I'm dealing with sine and e, and again anytime that I'm dealing with like this one in particular, dealing with e to the y, I'd have to multiply by dy dx, kind of using that chain rule piece to account for the fact that y is changing. So derivative of my first function, sine, is cosine x times my second function, which is e to the y, plus my first function, sine x, times the derivative of my second function. So derivative e to the y, derivative of any e function is just itself. But then again, this one I'd have to multiply by dy dx because I'm dealing with this derivative in terms of x, but this is a derivative with y in it. And then minus derivative of x squared is 2x, and derivative of 4 is 0. Okay, so before when we did implicit differentiation, I'm going to do this all in one step. I moved everything over to the other side, so I'd add the 2x, I'd subtract the cosine cosine x e to the y, and then I'd end up dividing by this quantity here. So divided by sine x e to the y. So you might have gotten to this point and you might have been like, oh, that's not a choice. So maybe my answer is none of the above. But we have to be able to recognize that this is mathematically equivalent to our answer D. So if I rewrote this function as 2x over sine x e to the y, and then minus cosine x e to the y over sine x e to the y, my e to the y's would cancel out over here. Cosine over sine is cotangent. I'd have 2x, 1 over sine is cosecant, and then 1 over e to the y is e to the negative y. So this is equivalent to my answer here of D. But again, I don't necessarily have to write it this way. Like on the free response, it'd be perfectly acceptable to leave it like that. But I have to be smart enough to recognize the fact that the AP test won't necessarily give it in the way that I've represented it, in the way that I've taken this derivative. So I need to be able to recognize the fact that it might end up being in a different way. So I have to be able to manipulate it, in other words. So all your simplification doesn't necessarily have to happen, but we need to be able to recognize and be able to manipulate to get to that spot. Okay, so let's start then with our function natural log of x. And again, before we actually find and I tell you the derivative of, sorry, I'll write it like, I'll write it later. So before I actually tell you the derivative of natural log of x is blank, I want to go through an exploration or to prove to you how you can actually get that. Kind of like we did for the exponential function, we use a graph. This time we'll be doing it algebraically, but we'll go over how to actually get to that piece. So in order to get there, I'm going to rewrite my function e natural log of x as a different form of the same function, so something that's mathematically equivalent. I don't know how to find the derivative natural log of x, but I do know how to find the derivative of its inverse. I do know how to find the derivative of e to the x. So instead of writing this as some log function, I'm going to write it as some exponential function. So to do that, to kind of get rid of natural log, how I do that is how I undo that is I use exponential. So I'm going to kind of raise both sides here to the e to write the mathematically equivalent to that part. So that would end up being e to the y equals e to the natural log of x. So these are mathematically equivalent because I did the same thing to both sides. On the right-hand side, e to the natural log of x, these are inverses of each other, so they undo each other, so I end up with just x. Okay, so now I'm dealing with an exponential function, similar to what we just dealt with here, e to the y. We're going to find now the derivative, because that was the goal, is to find the derivative of y, find dy dx. But this, again, is not y equals. It was at first. It was an explicit function. Now it's an implicit function. So I can find this derivative implicitly. So find the derivative of e to the y. That would just be e to the y. And then again, because it's implicit, I'd have to multiply by dy dx. And the derivative of x is just 1. So if I solve, I get 1 over e to the y. And that's great. But because we were given an explicit function to start with, I probably should end up with some explicit function or explicit derivative. So something all in terms of x. And we've done that before when we did our implicit functions. We just back substituted. So I know that y is actually equal to natural log of x. So I can take y out and write it as natural log of x. And again, e to the natural log, those undo each other. So I just end up with 1 over x. So if I was finding the derivative of natural log of x, my rule here is that it is 1 over x. So 1 over whatever it is. So natural log of x squared would be 1 over x squared, but because I'm dealing with something that's not necessarily just x squared, I'd have a chain rule. So be careful with that part, but the actual bones of it is dealing with 1 over whatever that is. We can apply that to the same principle of a logarithmic function. So natural log is just log base e. The difference here is that log base a we can rewrite as natural log of x over natural log of a. So if you end up doing and coming up with those rules, again the bones are there. It's still dealing with 1 over x, but we have to multiply by natural log of a in the denominator. So in other words, divide by natural log of a. Rather than for exponential, we multiply by natural log of a. In this case, since we're dealing with its inverse, we divide by natural log of a. So inverse function, inverse operation. So now that we have the rules for what we're dealing with today, let's do a couple examples. So again, we're dealing with a natural log function. Oops, I should write it as y equals. I'm going to find the derivative of y, so I'm finding y prime. I'm dealing with a couple different functions here. I'm dealing with natural log. I'm dealing with this x squared plus 1, so I've got chain rule. Let's start then with our outermost function because we work outer to inner. So the derivative of natural log is 1 over whatever it is, so 1 over x squared plus 1. And then we'd multiply by the derivative of our inside function. So our inside function is x squared plus 1. The derivative of x squared plus 1 is 2x plus 1, or 2x plus 0, I guess I should say. So 2x over x squared plus 1 is our derivative. Remember, all of our same rules apply. So in this case, we're dealing with x times the natural log of x minus x. This part here, since we're dealing with x times, this is a product rule. So when I first find my derivative, I have to use my product rule for it. So derivative of just x is 1, that's my first function, times my second function, natural log of x, plus my first function x times the derivative of natural log of x. So derivative of natural log is 1 over whatever that is, so 1 over x in this case. I don't have chain rule because I'm just dealing with the simple function of natural log of x, not natural log of x squared or natural log of x cubed plus 1 or whatever it is. And then finally, derivative of, if I keep moving on, derivative of minus x is minus 1. So I have natural log of x, and these cancel, so I'd have plus 1 and then minus 1. So those would end up canceling out, so I'd end up with just natural log of x for my final answer there. Do a couple more. We won't do a crazy amount. But we'll look at kind of all the different ways that we could see that happening, all the different forms of it. So for this one, we're dealing with, again, still some natural log function, but what we really have here is some function to a power, and then that function here is natural log of x. So we're dealing with the chain rule situation of the outside function being something to a power and the inside function being natural log of x. So I'm going to deal with the outside function first. So if I deal with something squared, take the derivative of something squared, I'd bring down the 2. And then I'd have that something to the first power. So natural log of x to the first. So I'll bring down the power, reduce the power by 1, but then multiply by the inside function's derivative. So natural log of x, that derivative we just learned today is 1 over x. So altogether, if I were simplifying this and writing a little bit better, I'd have 2 natural log of x over x. Let's make it a teeny bit harder. So I am dealing with natural log, obviously. I also have some inner function here, 10 over x, so I'm going to end up using chain rule. I'm going to write this as 10x to the negative 1 as that inside function, just because I know I'm going to end up having to take the derivative of it, and it's a little bit easier to write it that way. So let's see, my outside function is natural log, so I know that when I take the derivative of natural log, I end up with 1 over whatever this stuff is. So in this case, that's 10 over x. And then I multiply by that the derivative of my inside function. So my inside function is x to the negative, or 10x to the negative first power. So if I took the derivative of that, I would bring down the 1, the negative 1. So I'd have negative 10. And I'd reduce the power by 1, so negative x minus 1 is negative 2. So there's my chain rule. Let's see, this would be 1 over 10 over x is really x over 10. And this is negative 10 over x squared, so my 10's will cancel, one of my x's will cancel. I'd end up with a negative up top, and then x, just one single x in the denominator. Couple more. So these next couple we'll just be dealing with, again, some complicated cases, but then also dealing, because we haven't done with just straight logs up until this point, we've just been dealing with natural log. So the difference between natural log and log is that we do need that natural log of the base. The natural log base here is e, so when we multiply by natural log of e, it's just 1, so we don't usually in general write it. So this problem obviously has an outside function of log base 10, and I've got an inside function of square root of x plus 1. So rewriting that as x plus 1 to the 1/2 power might help us when we end up taking the derivative of that later, because we know we're going to have to. So let's start with the outside function. So derivative of log base 10 is 1 over whatever is in the, whatever the argument is, which is x plus square root of x plus 1, times the natural log of 10, or divided by the natural log of 10, however you want to say that. Appears in the denominator. All of that is the derivative of just the log part, so now we have to take the derivative of the inside function with chain rule. So derivative of the x plus 1 to the 1/2 power, I'd bring down the 1/2, reduce that power by 1. This actually is like double chain rule, because this isn't just x to the 1/2 power, but when I do multiply by the derivative of yet The extra inside piece, derivative of x plus 1, is just 1. So anytime that you're dealing with just like x plus something, it's as simple as that. But if this were like x cubed plus 1, I would end up multiplying by the derivative of x cubed here. So this actually really is 1, 2, 3 different functions combined that we have to have 1, 2, 3 different functions that we have 2 different chain rule pieces there at the end. But our second chain rule would just ended up being 1. Okay, so I could simplify this a little bit. I'd end up with 1/2. I'd end up with, so a 2 in the denominator. I have this natural log of 10 in the denominator. And this 1 over square root will end up getting multiplied by 1 over square root. And so those will end up kind of squaring each other. And we'd end up with just x plus 1 at the end. And last but not least, last one for today. Is 1 over log base 2 of x cubed. Okay, so again, I've got a couple different functions. I've got a log base 2. I've got this x cubed function, so I'm definitely dealing with chain rule. Even more so, this is not just log base 2, so I can't just ignore the fact that I'm dealing with 1 over that. So I actually have quotient rule here too, but for problems like this especially, I don't like to use quotient rule. Instead, I'm going to write this as log base 2 of x cubed to the negative first power. And so instead of using quotient rule, I'm just going to use power rule. So again, I actually have 3 different functions. I've got something to the negative first power, the log function, and the x cubed function. So I've got chain rule piece here when I take the derivative of the outside. I've got chain rule piece here when I take the derivative of log. So let's start with the outermost function. I should write it like this, y prime. The outermost function here is something to the negative first power. So if I take the derivative of the negative first power, I'd bring down the negative 1. My pen's running out. It's a good thing it's the last example. I'd reduce the power by 1, so I have now to the negative second power. And then I'd keep working my way inside. So the next inside function I have is log base 2. Derivative of log base 2 is 1 over whatever is the argument. So that'd be x cubed times natural log of 2. Since I'm not dealing with natural log, I'm dealing with log base 2. And then once again, I'd have to multiply by the derivative of the innermost function. So derivative of x cubed is 3x squared. So if I rewrite this kind of nicely, I end up having a negative in the numerator. This x cubed and x squared will end up canceling out. So I'll have an x in the denominator, so I have negative 3 in the numerator. I have an x in the denominator. I've got log base 2 of x cubed, quantity squared in the denominator, and I have a natural log of 2 in the denominator. So it should look something like that. So there we have it. So again, this actually is something like along with the derivative of like a to the x, derivative of log base a to the x is something that you'll end up forgetting. So we have a lot of different rules that we have handy right now. We need to remember all of these different rules for our next test. We need to remember all these different rules for AP test. Again, we're not going to get some cheat sheet or anything like that, so it's important to kind of make a list yourself and have a special place in your brain to remember all of these different derivative rules.